Hello everyone, welcome to this lecture video tutorial in Calculus 3. Enjoy learning.
Hello everyone, in this lecture video tutorial we will be discussing about infinite series of positive terms. After watching this whole lecture video, you will be able to understand that the convergence test and direct comparison, limit comparison, and integral test applies to series with positive terms. We also note here that since all the terms, as the title of the lesson suggests, are positive, the sequence of partial sums is increasing. And if it has an upper bound, the infinite series of positive terms is convergent. That's why, as you can see here, after the definition of the positive term series, the theorem suggests a clear manifestation of such phenomena. Moreover, let me remind you here with such passion in our previous lesson 2, 3, and 4, the convergence tests that we discussed here so far are fairly simple and have some special characteristics in order for the test to be applied. If somehow there will be a slight difference, or shall I say alteration, the test is not applicable even though they are very similar in nature. I will discuss that later in our discussion. Uh, Finally, this lesson will significantly help the students in their arsenal or bank of ideas with regards to their list of tests of convergence. That is, having a complicated term in the problems or exercises they may encounter, they can compare it with a simpler series whose convergence or divergence is known. That's an interesting idea to look into as you watch this whole lecture video. So without further delay, let's start lesson number 5. Hello everyone, welcome to our fifth lesson, which is entitled Infinite Series of Positive Terms. So for our first definition, as you can see here, uh, if all the terms of an infinite series are positive, then the series is called a positive term series. Okay, what does this definition mean? So to expound this definition, so notice that if you are given an infinite series, say this one, and if you expand this, a sub 1, a sub 2, a sub 3 up to a sub n up to positive infinity, what does this definition mean? So this term, each term, this one, okay, each term, if each term of this series are positive, okay, are all positive, positive, okay, positive, then this series is called a positive series. That's what it's mean. uh, uh, that's what the definition means. Okay, and please do analyze that if these are all positive, if our a1, a2, a3 up to an and so on are all positive, then notice that the sequence of partial sums is increasing. Okay, so can you imagine that we have 1 plus 1 half? So since all those terms are positive, then if you add up the sequence of partial sums, t1 is equal to a1, T2 is equal to A2 plus A2, remember that all of those are positive. Okay, so meaning to say the sequence of partial sums is increasing. Okay, please note of that. Okay, so that's definition 1. For this theorem, which is related to our definition, if you are given an infinite series of positive terms which is convergent, so if you are if the infinite series is a positive term series and it is convergent, then obviously the sequence of partial sums has an upper bound. No, not obviously. This means that uh, if the given series is convergent, a positive term series is convergent, then what will you do is that uh, if the sequence of partial sum has an upper bound, then that series is convergent. That's what it means by this theorem. Sorry for the first explanation. Okay, so all you have to do is to get the sequence of partial sum, and if it has an upper bound, then the positive term series is convergent. Okay, so let's try to illustrate this theorem. Okay, let's have this example. Okay, so let's have this illustration. Illustration. uh, Show that the series summation of 1 over n factorial. Your n starts from 2. Our index is 2. Is convergent using the theorem. Okay, what I mean by the theorem is this theorem. Okay, so this theorem says that in order for this series to be convergent, what we will do is to observe the sequence of partial sum, and if it has an upper bound, then this series is convergent. Okay, so let's solve this one. Okay, so let's wait for the program to respond. Sorry. So solution. Okay, let's observe the sequence of partial sums of the given series. Okay, notice, let's try to expand this example. So your n starts from 2, 1 over 2 factorial plus 1 over 3 factorial plus 1 over 4 factorial, and so on up to 1 over n factorial up to infinity. So as not to confuse with the notation, remember that the sequence of partial sum is denoted by T sub n. Okay, our n partial sum is denoted by T sub n. So basically you will write T1 here. Okay, T1 is equal to A sub 1. But notice in our given, if we write A1 here, this will be confusing. If we write A1, A2, A3, okay, it will be confusing. This is AN. Okay, since this is our this is our an. Then if you put 1 here, the Rn starts from 2. Okay, so what shall we do here? What our let's not confuse with the notation. Let's write the first term by a2, not by a1, knowing that a2 is our first term and a3 is our second term. Okay, so that's what we are going to do. Okay, so let's replace this one as, okay, 1 here. So let's replace a1 by a2. Okay, a3, a4, and then an. So from here, our first term, we will denote is this as t2. Okay, so as not to confuse with the notation. Okay, if you encounter a problem where n starts from 1, then you will use t1 as your first term. Okay, so let's move upward. Okay, let's wait for the program to respond. What happened? It's odd. Okay, so what we will do here is write t2 as our first term. Okay, which is 1 over 2 factorial. So this is the first term of the sequence of partial sum. So t2, again, why do we have to write it this way? The answer is so as not to confuse or to, yeah, that's right, to confuse with the notation. Okay, but bear in mind that this is the first term. Okay, a2 is our first term, a3 is our second term. Okay, we use only the notation. Okay, so as not to confuse with our notation here. Okay, a3, 1 over 2 factorial plus 1 over 3 factorial. Okay, t4, let's try another one, 2 plus a3 plus a4, 1 over 2 factorial plus 1 over 3 factorial, 1 over 4 factorial. Okay, so now let's write the end partial sum. Okay, so end sum. Okay, t sub n, a2 plus a3, a4, so on up to an. 1 over 2 factorial, 1 over 3 factorial, and so on up to 1 over n factorial. Okay, this is what we call our end partial sum. Okay, so again, let's wait for the program. And partial sum. Okay, so after this, since our topic is entitled infinite series of positive terms, and then as you can see in your module, you have read the topic, direct comparison and the limit comparison test, which is under in this discussion. So what we will do here is to compare. Okay, let's compare this sequence of partial sum to a known series, a known convergent series. Okay, so no, then compare the sequence of partial sums uh, to a known convergent series. uh, this known convergent series that I am going to compare to this sequence of partial sum is the geometric series. Why? I will explain it later. But observe that then compare the sequence of partial sums to a known convergence series. This one, summation of 1 over 2 to the n minus 1, where n starts from 2. Okay, then compare the sequence of partial sums to a known convergent series, this series. Okay, why our n starts from 2? As you can see, our n starts from 2. So that's basically what happened. Why this series? This is because the terms of this series compared to the terms of the uh, sequence of partial sums, these terms here are greater than or equal to these terms here of the sequence of partial sum. Okay, so let's try to expand this. This is 1 over, let's see if that's it's really the case. Okay, 1 over 2, and n stars 2, we have 1 over 2 square plus 1 over 2 cube plus 1 over 2 to the 4, and so on, 2 to the n minus 1, and so on. So when n is equal to 2, 2 minus 1, 1, so we have 1 here. When n is equal to 3, 3 minus 1 is 2. Okay, we have here. Okay, this series here is convergent. Okay, this is convergent. This is a geometric series, which is similar to remember that our geometric series starts at n is equal to 1. Okay, so this is similar to a geometric series. This geometric series, summation of 1 over 2 to the n minus 1, and starts from 1 to positive infinity. And as you notice, when n is equal to 1, this is 1 plus 1 half plus 1 over 2 square plus 1 over 2 cube, and so on, plus that. And the sum of this series is given by this one. This our a here is 1. Okay, our a is 1. Sorry, we have a mosquito here. I was not able to kill the mosquito. Our a is equal to 1 and r is equal to 1/2. So our formula is 1, which is a, over 1 minus 1/2, and this is equal to 2. Okay, notice that our summation uh, starts at n is equal to 2. So from here, this means that let's try it here. This is equivalent to 1 plus summation of 1 over 2 to the n minus 1 to positive infinity, which is equal to 2. So therefore our sum is, this is equal to 1. Okay, so just use this. Okay, transpose 1 to the right side and you have 1. Okay, let's wait for the program to respond. Okay, so why do we have to compare the why do you have to use this geometric series as a known series to compare this to compare the n partial sum of the series? Okay, notice that the denominator, okay, so the denominator, if you look at the denominator here, okay, so compare that one, this one also, this one, okay, and so on and so forth. You can have 1 over 4 factorial. You can compare it to this one. Okay, so notice that the the terms, okay, 1 over 2 factorial and 1 over 1/2, they are the terms in the geometric series is greater than or equal to this, to the terms in this of the nth partial sum. Okay, I hope you noticed that. But how do you know that as n becomes big, or as n approaches to infinity, the terms of the geometric series is clearly bigger than the terms of the n partial sum. Okay, please recall, if you recall your algebra. Okay, you can recall your algebra that if you have if you are given a what do you call this one, uh, a real number uh, which is positive, okay, and this real number satisfies this inequality, then the conclusion is the reciprocal is meaning meaning the inequality becomes reverse. Okay, so let's have an example. uh, if you have 5, say 5 is less than 7, says here uh, in this recall that 1 over 5 is greater than 1 over 7. So the inequality, sorry, the inequality will be reversed. So from here, let's try another color. So actually this is our A and this is our B. So from here, okay, so it says that this one. So if this is, if 7 is, if B is bigger than A, then it says that 1 over 1 over A is greater than 1 over B. So this makes sense also if you have a equal here. Okay, so if this is, if 5 is less than or equal to 5, then this is true also. Okay, but anyway, just to make it similar to our discussion, this one is they are equal. Okay, but the rest is not. So that's how you are going to use this recall number 1. And also, okay, let's wait for the program to respond. Another note here, note number 2, that n factorial is, if you recall your statistics, this is n times n minus 1 times n minus 2 up to 3 times 2 times 1. Okay, so this is basic, this is in your statistics. Okay, we know that where's that one, we know that n factorial is greater than or equal to 2 to the n minus 1 for all n greater than or equal to 2. Okay, so what happened here, this is our A. Okay, this is our A and this is our B, or no, this is our B. What happened, let's wait for the program to respond. Sorry, this is our B and this is our A. Okay, so what happened here is that we can write it in reverse order. This is 2 to the, can write it this way so that it will become similar to this notation. 2 to the n minus 1 is less than or equal to n factorial for all n greater than or equal to 2. And this is our B, this is our A. Okay, this is our B and this is our A. So this implies that 1 over 2 to the n is greater than 1 over n factorial, or all n greater than or equal to 2. Okay, so let's see when n is equal to 2. So we have 2 minus 1 is 1, so 2 to the 1 is 1. 2 factorial is 2, so we have 2 is greater than or equal to 2. When n is equal to 3, we have 2 to the 3 minus 1, 3 minus 2, 4. And then 3 factorial is 6. 3 times 2, we have 6. So this is clearly true for all n which is greater than or equal to 2. Can we include 1? 1, 1. If 1, zero factorial. Okay, this is true for when n is equal to 1. Can I uh, erase this one and start with 1? Okay, what happened here? What happened to the symbol? Sorry. Let's wait again. Let's wait again for the program to respond. Okay, so let's erase this one and erase also this one. Okay, then let's delete this. This is 1 over n factorial. Okay, anyway, so it covers all the terms when you have n greater than or equal to 1. Okay, so we can see here that the terms of the geometric series are clearly greater than or equal to the terms of the nth partial sum, as you can see in our discussion. Okay, so actually you are comparing. Okay, you are comparing. Then after this, this means that our, what we call this one, this means that the geometric series summation of 1 over 2 to n minus 1, where n starts from 2 to positive infinity, the sum is equal to 1, then it means to say that the upper bound for the sequence of partial sum is 1. Okay, so therefore let's try to write the conclusion. Therefore no, not therefore, let's say notice that the, again, let's wait, what happened. Notice notice that the, what do you call this one, the nth partial sum 1 over 2 factorial plus 1 over 3 factorial over 4 factorial plus dot 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 up to 1 over n factorial, that's what happened. Let's move upward. Okay, is less than or equal to the sum of this geometric series. no 2, n starts from 2. Again, let's wait for the program to respond. What happened? N starts from 2 to positive infinity, which is equal to 1. Okay, so this implies that the sequence, okay, this implies that the sequence of partial sums has an upper bound which is 1. Okay, but it doesn't say that the what they call this one, the sequence of partial sum, the value of this one is equal to 1. It doesn't say that way. Okay, it says that the upper bound uh, of this sequence of partial sum is equal to 1. Okay, so we have shown here in our theorem, sequence of partial sum has an upper bound, then the series is convergent. Okay, our given series. So by the theorem, let's wait again for our program to respond. So therefore by the theorem, uh, what happened? Let's wait again. The given series is convergent. Okay, so all you have to do is to find a known convergent series. So the known convergent series that we discussed before are the P series, okay, the geometric series, and we have the harmonic series, which is part of the P series. Therefore, by the theorem, the series summation of 1 over n factorial, n starts from 2 to positive infinity, is convergent. Okay, and so using the theorem, later on we will be able to find the sum of this series, maybe later. Okay, so what have we noticed here is that uh, the given series that we are going to show, that it is a convergent series, we compare it to a known series which is convergent. Okay, which is actually, this theorem is a particular case of our next lesson. Okay, which is the this one, the comparison test and the limit comparison test. Okay, so please do remember that what have we discussed before about the theorem. That theorem is a particular case of this a name test. No? It has a name, which is this first theorem is what we call the comparison test, and the second theorem is what we call the limit comparison test. Okay, so which is our next discussion. Okay.